The broadcast is now starting. All attendees are in listen-only mode.
Well, thank you everyone for attending today and joining us. I think we have a great webinar set up for you guys, very informative. Please note any questions you have during the session, please type them into the chat panel and we will get to them at the end of the session. Going to first do a quick overview of Alliance for those of you that don't know us, and then I'm going to hand it to Brent, VP of Sales of Kaelus, and he'll take it from there. My name is Michael Short. I am the Director of Wireless and Name Building and DAS for Alliance. I'm based out of Calgary. Alliance, we're a leading distributor of wireless infrastructure products. We have an amazing supply chain solutions, world-class inventory, warehouses throughout the U.S., Canada, and CALA, and we have a great staff of industry veterans. Some of the solutions that we do provide, infrastructure products, tower-mounted products, fiber solutions, custom fiber to the antenna, indoor and outdoor DAS, microwave backhaul, and encompassing that all is our supply chain solution. Some of our customers are carriers, contractors, integrators, and OEMs, specifically focusing on carriers and contractors and integrators. Specifically on our wireless infrastructure side, we are the experts in PIM, part of the reason why we're having this session today. Fiber to the tower, fiber to the antenna, indoor and outdoor DAS, as well as our supply chain solutions. And some of the DAS solutions we encompass are small cell, as well as cabling, antennas, testing, as well as active and passive gear. Just one note to put in your calendars, our next session is going to be PIM and DAS networks, hard lessons learned, sort of the next step of this webinar. We're going to have Solid on, as well as Kaelus that's going to join us. And at this point, I'm going to pass it off to Brent.
Alrighty. Okay, great. Again, my name is Brent McMurray. I'm the Vice President of Sales for the Americas for Kaelus. I'm going to do, similar to Mike, I'm going to do just a quick overview of Kaelus, who Kaelus is, and also do a quick introduction to our new passive intermodulation test set. With that, I'll jump right in. Real quickly, Kaelus is part of Smiths Group. Smiths is a very diverse company based in London, very diversified through detection products, John Crane, which is oil and gas, Smiths Medical, Interconnect, which is where we reside, and FlexTech, which makes engineered flexible conduits for gases and other products. About Kaelus, we design and manufacture a wide range of RF products, from our RF conditioning products, which include inline filters, CMAs, combining solutions. We also do our PIM test instruments, which is the heritage product of Sumatech, which most people know our PIM product from. That includes our bench PIM and our portable PIM unit. We also have a site services group as well, too, that is headquartered here in Denver. Real quickly, I just want to talk about our new product for portable PIM testing. It is our IPA. I do want to preface this by saying we've delivered over 3,000 of our IQA product, which is our portable product as well that requires AC power. We'll continue to produce that product and manufacture that product. There's just been some requests by certain carriers for a portable product that can be carried to the top of the tower. So want to just do a quick overview of the product. It'll take about 2 or 3 minutes. As you can see from the picture, it is a highly portable and ruggedized product, ideal for top of the tower. It includes an iPad mini for safe hands-free dynamic testing. So the PIM tester itself does have a Wi-Fi connection and connect to any internet-based product. So it does come with the iPad mini, but it can connect to any iPad or any smartphone that you may have. This unit will be 2 by 20 watts. We'll continue with the 2 by 20 watt as called out by the IEC. And Tom will talk a little bit more about that in his presentation. It is fully battery powered. It has an onboard touchscreen interface for local control, and it has our leading report generator, which is we work with in developing with all the major carriers. It does have variable output power, which is something that we built into this product. In fact, some of our friends up north require lower power testing for PIM, so we've built the capability of this new portable unit to go from 20 dBm to 43 dBm. I won't get too much into the specifics, but it obviously has a very strong residual PIM. It is ruggedized and lightweight, as you can see. It's only 26 pounds and remotely controllable. The arms of the unit can fold into various positions so that the unit can be set upright on its back, but again, mainly keeping it out of the elements and off the ground. It does have hoist clips as well too, so that it can be hoisted safely to any tower. In the initial launch of the product, we are accepting orders now. Alliance obviously is our partner for this product. But we are going to be selling a 700 version, an 850, a 900, and 1800 for our friends in Europe, and a 1900 version for the Americas as well. And with that, I will turn it over to Tom Thompson, who will discuss the aspects of PIM in a DAS environment.
Thank you, Brent. Thank you, Mike. I'm going to begin today's discussions by basically saying a lot of the information that you'll see in this presentation has been gained through field experience. PIM and its actual discussion about the background, the theory, the why it happens, while interesting, is not nearly as valuable as the field experience gained in constructing a DAS and making it perform in an environment where PIM is not as big an issue as it should be. Next slide. We're going to have an agenda quite quickly. We're going to take about 45 minutes to go over this. We'll step one through initially a review of PIM. My assumption is that if you're on this call that you have some idea of what PIM is. There is some possibility you need more information. Certainly reach out with a question and we'll get you more information up to and including full training on PIM testing. I'm going to offer some design guidance. I'm a little bit reluctant to tell you this, only in the sense that my job does not require that I design DAS systems, but instead that I go in and evaluate DAS systems that have already been designed and try to determine what things, if had they been done differently, we'd have had better luck with the PIM performance of the system. I'm going to talk about training. Quite often what I find is that a team showing up to try to install a system, any system, whether it be a macro site or a DAS, needs to understand what things that they do in the field actually affect the PIM performance and how can you train before you get to the site and wind up spending time that would have been better invested back at the office. Construction methods, what things do you do with a good design in hand? How do you get into the field and get construction done in such a way that PIM is not an issue for that particular system? This is probably where most of the time is spent at this time. It is a challenging situation to construct a PIM good system. Then we'll have some time left over for questions and answers. As has been said earlier, you type them into the chat screen. We'll get back with you even if we don't answer them during the live session today. A quick review, and indeed this is very quick. PIM is interference. It's one of many interference sources. If you're putting a DAS into a hospital, you're going to have a number of other interferers in the system. But PIM is one that we can control during the construction and design phase such that we don't have to worry about it if we do it right. The other ones are going to be something we're going to have to hunt down and resolve on a case-by-case basis. In the case of a DAS system, it's quite true that every DAS is unique. There is no standard DAS. There's no cookie-cutter step and repeat capability because the structures themselves do not lend themselves to a step and repeat sort of methodology. There are common themes, but there are no single DAS type performance. To think of PIM really as noise is the best way to think of it. It is generated by the fact that you have traffic. The downlink signals, the transmit signals, are combining in a nonlinear fashion to create interference in the receive or uplink band. This is done by the components, the way the components are put together, and even the environment in which you've mounted the DAS or the DAS antenna such that it could create PIM. Again, multiple frequencies. In the case of testing for PIM, we'll use 2 test frequencies. That's all that's really required to indicate a nonlinear performance in the system. And it will create PIM both above and below those 2 transmit frequencies. Depending on how your spectrum is distributed or what particular DAS system you're on, it may be the high side or the low side PIM that becomes the interference that you're going to see. Again, as we cross the globe, different spectral plans lead to different concerns about which side of the PIM is going to be an issue on. What we're going to talk about is the difference between linear. 2 good metal-to-metal contacts creates a very straight line or linear current to voltage graph. Nonlinear means that line's no longer straight. I can't take a single ruler and put it on the line and cover that entire line. Typically, it's going to be caused by some version of a non-intimate metal-to-metal contact. In this particular depiction, we show something that looks like a micro-arcing, a little lightning bolt. That's the nonlinearity. As the voltage increases, the current's going to change in a way that's not a straight line. Initially, it may not change at all, and then we'll reach a point where it changes rapidly. This could be where arcing occurs or where a diode junction begins operating. It's not linear. It's not a straight line. It's going to change such that when we apply the RF signal, we're going to get new frequencies. The metal-to-metal contacts we're going to discuss at great length because most often it's poor tightening and cleaning of connections that get good intimate metal-to-metal contacts that are controllable when we install a DAS. This is something we have to pay attention to. Arcing can occur across micro gaps. Again, these gaps can be caused by cracks, surface roughness, swarf in the connection, or the fact that we didn't tighten it. In the case of a DIN connector, a loose DIN connection will automatically PIM. Oxides, other things that can impede the current flow also need to be considered. Again, this is the cleanliness aspect of the DAS PIM checking. Anything that's a diode is going to be a mixer. Anything that's a mixer is going to cause interference. That's really where we're looking at. This is self-inflicted interference that we're going to try to resolve. Again, we talked about 2 frequencies were involved. Why do we care? Those 2 frequencies spread out. IM3, IM5, and IM7 spread out. Their amplitudes get lower, but they spread out everything over frequency. They reduce the coverage, the capacity, and they lead to slower data rates. In the DAS environment, it's the slower data rates that first become apparent. Again, the interference takes up spectrum. You have to change your system performance such that you can let your real desired signals through. Elevating the noise floor is the first signature. We'll show a slide in just a moment where what that might look like. You can't see your customers is really what it comes down to. In many situations in the DAS, the desired high-speed performance is not achievable in the real world. That reduces revenues. Primary causes are design. Design using PIM generating components, it has not gotten out of the system yet. There's still designs that include lower cost components that have not been specified for PIM performance, and at that stage you will not be able to construct a PIM performing or a PIM good DAS because the components themselves limit the system performance. If the design has been done correctly and has all high performance components that have low PIM levels, you can still put it together in such a way that the construction quality creates the PIM. This is really what we'll want to address at this particular conversation the remainder of the day. Here again is a quick review of the noise floor. What you'll see initially is that the initial noise floor with no RF turned on, we're just looking at the noise floor of the system. This is the noise, the thermal noise for the system. You can see it's relatively flat across this with a slight roll off at the edge where we're seeing the filters in the receive band. We apply LTE RF power from an E node B. We look at the spectrum again in the receive band only. Again, we applied the downlink power, and we're looking now at the uplink. And what we see, it's not flat, means there are PIM issues. That would be the yellow trace that you see in this particular spectrum graph. This is not flat because if you remember from the previous slides, the IM7 was broader in spectral extent than the IM5 and broader still than the IM3, and it's the addition of those together into a power root mean square power method that causes this to not be flat. You can use this in a passive or an active DAS. That means that I can go to my optical modulator output on the receive port and look at the noise floor, or I can go all the way back to the eNode B and look at the receive-only port if that's available to us. These are important places to look, and it allows you to do some simple debugging if you have this capability available to you. In terms of design, well, all I can recommend to anybody who's having to design a DAS at this point in time is use PIM-rated components. It's something that, again, more and more vendors are offering components that have a specification line that reads PIM. You need to choose those components. They are available for every component used in a typical DAS. Again, if you do an internet search, you'll have no trouble finding a number of vendors for each of those types of components. A splitter, quite a few people are out there. They have measured good. They're a component that's a staple in the design, so it's not a hard time to find them, and there are more and more entering the market space every day. Antennas is a place of great concern. Initially, DAS antennas were not measured for intermod. That has changed, and more show up on the data sheets. Again, operators are requiring that the antennas perform. The antennas are going to come back up at a later state in this conversation because the antennas themselves may be good, but where you position the antennas is going to be critical in determining the PIM performance. The connectors, at some point in time you're going to have to come to terms with the fact that the DIN connector is a superior connector, but it's also more expensive. A complete DAS based on PIM is not achievable at this time, or not financially achievable, and there are a large number of connector manufacturers working the issue of either a mini DIN or improving the Type N connector's performance. Type N can perform well versus PIM, but you have to be more careful with it. It is not purposely built as the DIN connector was to address PIM issues, so there is some extra detail or attention to detail required to get that to be successful. If you can, use solid outer conductor cables. A number of DASs have been installed over the course of time that use braided cables. We have attempted in a number of situations to achieve good performance using a braided cable. With regard to PIM, the braided cable is very difficult to get to operate. That said, you will see some braided cables coming up where we will discuss how they achieve good PIM performance, but they are not generally available for your major distribution paths in your network. Again, can't say it often enough, if you can use DIN 7/16, use that connector. It has been optimized for PIM performance, among other things, but I understand it is expensive. A lot of times we'll find them deployed predominantly in the equipment room, and then as we get further into the DAS, the Type N connector will again return into dominance. Avoid high-power RF terminations. They're not PIM rated. These are used on hybrids, typically 2x2 or 4x4 hybrids, for the unused output ports to make sure that you have either future expansion capabilities or that you just don't want to use that port. You're using a 2x2 where you could have used a combiner or a diplexer. In those cases, those particular terminations generate PIM, and that PIM immediately heads back to the eNode B and jams the entire sector, and the entire sector is basically difficult to get any kind of performance out of. A very common problem, one that's being addressed by, again, a growth in the number of terminations you can buy that are high power but are PIM rated. Again, look on the data sheet for that specific data line. Inline attenuators. We're at a state at this point in time where many macro site base stations are used to create DASs, and so they turn up the power to a level well beyond what's necessary, and then they proceed to attenuate the RF power level down. If an inline attenuator is used to do that, and it is a PIM source, again, much like the RF termination, high power RF termination, the entire system, unless the transmit and receive paths are separated completely, will see PIM. In the case of a MIMO system, that's going to be something that's impossible. So for future-proofing your designs, try to avoid inline attenuators. They're not set up in such a way that you can avoid the creation of PIM getting back into your system. Diplexer filter combining is a much better way to go. In this particular case, it's going to basically combine things together without having the need for any of the high power terminations, and possibly you can avoid some of the attenuators. Again, there are lots of ways to approach it. We've got things we can tell you at a different date. In the equipment room, one of the things that I find, again, it has to do as much with construction as with design, is that you want to keep a clean layout. There's nothing better than to go into an equipment room where everything's been laid out in such a way that it's a repeating block diagram. I can touch each piece, I can apply a process, I can succeed on that block, if you would, and then I can move to the next piece of the block diagram and apply the same procedures, the same processes, and succeed. Again, in the field, when you're trying to construct a system or build a DAS, repeating the same steps over and over leads to better and better successes. You begin to converge, especially when it comes to PIM and trying to remove that from the system. You can see here, there's 3 of the 7 BTSs in this, or eNode Bs in this particular DAS, side by side with their combiner components. They did use PIM-rated hybrids. Again, as you walk into any particular design system, you should be able to ask for the data sheets for each component and look for the performance you expect to get. One of the things we'll talk about later is what power to test at. You also need to check the power capability of each of these components such that you don't apply too much power and destroy components as you go through the system. You can see the hybrids, again, in this particular case, combining 2 paths together into a single path into the DAS. High power terminations creates PIM, the output of the 2x2 hybrid. In this particular design, we were not able to get success in reducing PIM because of that specific component. Again, it's at the unused port of the 2x2 hybrid, as I had mentioned earlier, that's sometimes used. We did use some components to remove that and show that it would work, but it is a more expensive component. So low power or low PIM high power termination is more expensive than the other. As part of the design block diagram, please provide information to your contractors as to what you'd expect them to do and how they do it. One of the questions we're often asked is, should you test as you go? It has been determined, especially in the case of a DAS where you're building cables on site, because that's just the only way that's possible, that you need to be able to test each cable as it's constructed and move forward with a plan. In order to implement a plan like that, what you're going to do, especially in, say, the equipment room, is to have labels. I want to test at point DX2. I want the label to come back and tell me what the PIM performance is from that point looking through the system. I may find that I want to test just the jumper 1. I need to provide the ability to label that jumper. So when I get that information back, I've communicated what it was in the block diagram that I provided, this system plumbing diagram, such that I can correlate the PIM data that was taken to the actual physical location of the component or the system or the branch or sub-branch that was tested. Again, we can march through the entire process. In this particular case, what we're going to show is a series of labels that were used in determining that the load on the 2x2 hybrid was the source of PIM. We will march through the system, simplify the system, and break it into smaller pieces. If you have PIM, you'll need to do some version of debugging that reduces the network into smaller and smaller pieces until you can identify where the PIM source is and try to remedy that particular PIM source. It may be a bad connector, a bad cable, or a bad component. Those are things that you have to be prepared to look through. In order to succeed when you get to site, you have to have some training such that when you arrive, you can have some feeling of what you're looking for when you walk through the building. Can you identify potential sources? What things do we need to be careful of? And this applies to the design team, who should walk through a building and determine locations where they believe they're going to put an antenna and what are the risks of putting an antenna in that location, whether it be the landlord doesn't want an antenna placed there, so it's aesthetics, or is it going to be something where we're familiar with the construction of the building, and this particular area over here is always going to be difficult to get the antenna to meet its PIM specifications, or is it something related to the actual routing of the cables? There's a number of things that can be seen once you become familiar with what causes PIM and what you can do about it. Design team must focus on component selection. As I mentioned earlier, there is no success if you start off with components that cannot pass PIM. So again, as you begin any design project, look at each piece in that block diagram and find low PIM components to be used. And we'll get back to that numbers of times. Plan for PIM surveys. Many times in a DAS, you'll do a propagation study. You'll walk through the building to make sure that your models for coverage are accurate based on the actual construction of the building as opposed to the modeled construction of the building. Are the walls properly modeled? Is the expectation that I have of a certain amount of coverage actually being realized, or am I having some difficulties and I need to adjust? Well, the same thing's true with PIM. You need to be able to walk through the building, check locations where you believe you're going to place an antenna based on whatever criteria you've used to choose that location, and see if you can get a PIM-free location. You must design the test for the site. Every site, as I mentioned earlier, for a DAS is different. You must define what test levels you want to use. Some operators prefer to test at full power throughout the entire system. There's certainly nothing wrong with that. It is going to be a rigorous test. Others prefer to drop the power level depending on the location in the system that's being measured. This is sometimes considered for safety. There's various reasons. Again, I am aware of them, but I cannot give you guidance. You need to speak with whoever's having you design the DAS to make sure that you're doing tests that are specific to what they have in mind. At the end of the day, the DAS is being tested for construction quality. The actual performance is going to be indicated when they turn on, in this particular case, let's say the LTE system and the KPIs are met. That's really the final criteria as far as an operator might be concerned. You need to have what transmit power and what IM3 level. When you speak about PIM, there's always two pieces of information that are required. One is how much PIM, either in dBm or dBc, based on how much power did I put into the two tones. Is each tone 20 watts? Is each tone 1 watt? Both of those are particularly often used and are useful numbers. Certainly you need to have both those pieces of information. You're not giving a complete specification of what intermod that you're trying, or level you're trying to reach. If you look at data sheets, the international standard has been set to 2 by 20 watt tones will be used in every case, and then the specifications are going to be either in dBm or dBc. Those we can sort out at a later date. Construction teams must focus on processes. Everything that you do at the site has got to be scrutinized. Everyone has to share what the best practices are so that you can get the entire team working on the same processes. Quite often this relates to how do I put my connectors together? How am I tightening my connections? Is it a type in? Is it a type DIN? Do I use a torque wrench? What do I do? How do I place an antenna? How do I know that's a good place to place the antenna? A series of things like that. In the course of doing any DAS, each team is going to gain experience that will make the next DAS that much easier to do. You need to be able to recognize PIM sources. In the cable construction, nickel plating, which is a design concern, in many of the type N connectors are like almost all connectors start with a brass body that's then possibly nickel plated. The nickel plate provides a good surface for the silver plating that follows to get good conductivity. The difficulty is nickel is a magnetic material with a nonlinear property, hysteresis, that causes it to generate PIM. They can be found in many DAS systems, and they may be required to replace all of your connectors because of the plating that was used. Again, a legacy system can be quite difficult to debug and may require a great deal of expense. In the design process, just avoid using nickel-plated connectors. They'll be specified for PIM performance, and you'll be able to tell that they don't have nickel plating. This is particularly important at the lower frequencies where the skin depth of the RF currents is going to be such that it's going to get deeper into the plating system and possibly excite the nickel to create intermod. Loose connections, again, every connector's got a diagram that comes with it or a piece of paper to instruct you how to build it. Follow those instructions. If they're not tightened properly, they're going to be non-functional with regards to PIM. Preparing the cable terminations, how you cut the cable is critically important in a DAS system, especially with plenum-rated cables. This is a cable that was used in an outdoor site, so it's not plenum-rated, but you can see from the picture that there were quite a few mistakes made in the preparation of this cable. Anything from the cut being made such that there are jagged edges to a situation where the cable was not kept clean and the mating surfaces are winding up with plating that needs to be dealt with. Improperly and misaligned parts, as we showed in the first slides, are critically important. You need to make sure that they're all set up correctly. Metal chips and shavings, which show up as small bits of cable that were cut with a hacksaw for whatever reason, always wind up inside a cable. And a plenum-rated cable is they're more difficult to get out and clean than they are in the foam cable that you see above. But again, avoid cutting if you can by using a device that cuts not with a saw blade, but instead with a device that saws it into, or not saws it into, cuts it into with a straight edge. Antenna placement, we've talked about this at length. Here's a typical example in a garage, a parking garage. That particular antenna placement was not particularly bad, but to be fair, you need to test every position. One thing that is certain about PIM is if it's near an antenna near rusty metals, loose bolts or brackets, or has loose mechanical fasteners, is the potential for PIM. There is no guarantee one way or the other that you can avoid PIM. Experience is just going to be your only guide. Overlapping metal, which is typically seen outdoors, please keep in mind that an outdoor DAS, the vents for AC, the rooftop flashing for a thing is going to often cause PIM and is going to be difficult to avoid. What you'll do is you'll position your antenna such that those particular sheets of overlapping metal do not see much RF exposure. Connections to the cable, cut it with, I call this a pipe cutter. It's bought at a typical hardware store, big box hardware store typically. Used to cut PVC pipe, has proven very useful for cutting plenum rated cable. It does give you the ability not to create metal shavings. This is very critical again with using the plenum rated cable. I would further suggest that if you have any thoughts or doubts about metal shavings being created, please hold the plenum rated cable in such a way that anything that is created will fall down below it. So basically hold the cable above and pointing the opening down such that anything that's created will fall away from the cable and not into the cable. Slicing tool, not a saw. Dynamic connectors. When you're looking at your connectors, we talked earlier about the use of connectors without nickel plating. Also check to see if they're dynamic PIM rated connectors. What this means is, and we'll talk about it at length in the future, is that it's not good enough for the connector just to go on there and if you don't touch it, it'll pass PIM. You need something that's going to be able to withstand the physical challenges it's going to see in the environment. There are a number of different things. Outdoors, it's obvious that the wind and the rain can cause physical mechanical stresses on the cable. There's just as many things that cause stresses in the building environment, though not quite as obvious. Vibration from various infrastructure, elevators specifically, can actually cause motion of the cable with respect to the connector, and that can lead to PIM at a future time. Again, dynamic testing is what's required. Inspect for burrs and contamination. Again, we say it over and over and over again. You have to have clean cuts. You have to have everything removed from the area you're going to put the connector on. The manufacturer's instructions are going to say these things just like I'm saying these things. Please follow those carefully to get success. No known manufacturer is shipping product that doesn't work if done correctly. That said, doing it correctly in the DAS environment sometimes is more challenging than the manufacturer might have anticipated. Tighten them. You can. Make sure you show up with the proper wrenches. You need two. Make sure you have two in hand. Do not try to hold it by one in your hand and one with a wrench. You just, no matter how much you think you are, you're not going to be able to do that consistently. Two wrenches, again, properly tighten the connections. If you have access to a warehouse, I would suggest that you build a small section of a DAS to train your team to understand what things they might run into. In this particular case, here's a MIMO test fixture for 3 antennas. Specifically, what we're going to be looking at is a sub-branch. Again, when doing PIM testing, if you have to do it after the fact, you're going to need to break it into smaller pieces to isolate problems. If you're constructing, and this is the initial PIM testing, please consider building backwards from the antennas and testing as you go. This will give you the ability to determine if you've got a PIM problem, if you have return loss or insertion loss problems due to incorrect installation of the splitters and the antenna, whether or not its location is creating PIM. You can do the antenna test here. You can find out what things you can do in this particular case by moving it around and seeing what affects it. Do try to do this out again before you get to the DAS. Get a feel for what's possible. Each antenna is going to act differently. They all have different patterns. You're going to find that PIM is generated where the RF field is high. If the patterns change, that's going to be a different place. Cable construction, before you get to the site and start building cables, it's good to know that you have confidence in building a cable with the type of cable and the type of connector and the tools that you plan to carry to the site before you get to the site. A lot of time can be wasted by trying to spend learning on-the-job training time when you're at the site. Test as you go. Build it from the antenna back. It's a lot of work, but in order to get it right, you're going to have to do this to some degree. We've been surprised as an industry as to how sensitive the antenna location is with regards to PIM, even at low power levels. Build sub-branch. How am I going to report back to my customer? How's the report work? If I've got a design team who's given me guidelines on how to report and what reports they want, this allows us to see how we're going to do that in the field. Again, you want this to be second nature by the time you arrive at a DAS and you've got many floors to do and little time to do them. How do you test a component? 100% testing of the components in the field is not practical. You should expect that you bought a good component and it should work, but you need to know that if you have somehow achieved a PIM problem with a component that was passing at the factory, you need to be able to isolate that and know how to test it and how they might have tested it. Certainly keep your eyes open for stuff like that. It happens in the course of handling components and shipping them. Cables are the largest problem, again, because they represent to some degree a fair amount of complexity. You have to properly connect two connectors on each end, and then the cable itself could be damaged in some way. Again, if you've found yourself in a situation with a braided cable, you're going to have to study how you're going to get that pulled off. Putting the components together, as I said earlier, perfect components put together incorrectly won't work. So once you've got good components and good cables that you've constructed, you're going to have to be aware of how can I put that branch together. This is where you're going to learn how do I tighten the connections, do I torque the connections to a certain level. A number of people have found that the end connector performs better for PIM when they tighten it a little above the standard specification that comes in the data sheet. We have used steel wool as a PIM source in front of an antenna. It makes an excellent PIM source. When applying power at plus 15 dBm, we're seeing minus 70 dBm of PIM noise at an IM3 level, so it's a huge source of PIM. It's also quite true that it's not hard to find a similar type of level in the field. What this allows you to do is to see what it looks like when you're testing a system. Again, if we go back to the previous slide and think about the three antennas, if I put a PIM source on each of the antennas, how does that affect what I see at the measurement, at the test point, and can I get something from that data that I can identify it? Is the antenna particularly sensitive? You're going to find, again, with this particular thing, using steel wool is very sensitive to PIM. If you have a question in your mind about how low a power level do I need to test at, this will help you make a measurement and convince yourself that you can go as low as you want to go, and you'll still see intermod. It will be system impacting. It will be larger than the customer would like to see because it will impact their LTE performance. If you've got multiple ones, figure out what they look like. It turns out that they're going to add together as a vector, so you're going to see some that are going to add and make the PIM level higher, and then you have another one that shows up in a specific phase relationship, and it makes it look like the PIM is lower. This is something that we actually take advantage of to find out where the PIM sources are. This is very similar to what you see with return losses. The input cable and its motion. As you see in this particular picture, the blue cable, which is the feed, the pigtail to the antenna, is a braided cable. In this particular case, the braided cable has been tinned such that the outer jacket is more of a solid metal. It's not a very robust solid metal like a solid copper conductor might be, but it is a solid thing, and it does pass intermod performance unless it is flexed beyond its normal constraints. So for instance, that tin plating that's in there can fail at some point if it's being manipulated a lot, which can quite often happen in handling or placing the antenna in its final location. So do be aware of what's the effect of that. Understand that this cable getting in front of the antenna might often cause intermod also. So again, it's just an experience that you're going to learn, again, in the warehouse before you get into a site and have to learn it under fire. Low power, I mentioned it earlier. If you ever wondered what's the lowest power level that I need to go, this is going to show you exactly what happens. You can test this antenna. This antenna will pass at 2 by 20 watts, 43 dBm. It will also fail with the PIM source of steel wool on the front face of it at 2 by 15 dBm. So it's a very wide range of IM3 is created at the lower transmit powers, which was not expected by much of the industry. Again, testing as you go. You need a first pass success. There's nothing more difficult than trying to debug a DAS system because of the level of complexity, the number of interconnects, the number of potential problems with things outside the system, outside the antenna, a large number of other interferers. If you can pass as you build it, you're going to keep your life a lot simpler, and finish up sooner. Have a plan and work the plan. Again, the plan should be revised after every dash to help gain information from what you learned in the dash you just completed, but have a plan to follow it, and make it mark up at each time. Train to follow best practices before you arrive. Refine the best practices when you get done and modify them, but make sure that you know before you go in the building that you are going to be making cables correctly. You're going to be placing antennas in ways that it makes sense to pass intermod. Tools, you can't get into the field and pull out the gas pliers and use those in a system that's going to be tested for PIM. It's very challenging to get the consistency that you need. Have the proper tools for cutting and preparing the cables. Again, it seems like a little bit of over the top, but when you're talking about intermod, it's those types of preparation with the proper tools that get you a success. Have spares. There's no such thing as 100% successful. Even though it's tested 100% of the time, you will have a few of the components not pass intermod. That's just the way the world works. When working with the equipment, don't saw things. We've talked about that at length. Clean surfaces with alcohol wipes and compressed air. You cannot clean enough or make sure that things aren't in there, because again, once those are trapped in the mating surfaces or mated surfaces, they become much more difficult to clean back out. Tighten every connection properly. I will give you a heads up. There are some questions still in the contractor community as to whether or not tightening connections is staying tight over time. There is some question about the type-in connectors working for you over the course of time. Further information needs to be gathered on that. The DIN connector, once it's torqued correctly, it does not come loose. This is a good case of, it would be nice if you tested as you go. In this particular case, this has all the worst situations done here. We have a braided cable. They're the largest source of PIM. It was a crimped on connector. It wasn't crimped on properly. And it's got a knurled connector, no flats so I can tighten it correctly. This particular connector, because it was a poor choice and it had already fallen off, was replaced and resolved that PIM issue. But these are the types of things, just by doing a dynamic test, this particular connector, which had passed return loss testing, failed PIM and fell apart when I actually put a little bit of mechanical pressure on it. It is process sensitive. You got to cut it right. You got to tighten it right. You got to clean it right. Again, in this particular case, we started off with the wrong cable and the wrong connector, so we replaced the entire subassembly in this particular jumper. On-site construction requires on-site PIM test. Each component that you're getting that's pre-PIM tested was tested at the manufacturing location and sent to you with a piece of paper typically that tells you that it has passed PIM. In the case of a cable that you made to cut to length or to pull through a wall or any other particular situation, but it was built on site, the only time it was tested for PIM is on site. While it is true that you would like to believe that following process would give you a 100% guarantee of passing PIM just by following construction details, it is not proven to be the case, and that process sensitivities are still enough that you need to test 100% of the cables built on site while you're doing the construction. The best time for corrective action is when the cable is assembled and installed. The very best person to do that corrective action is the person who made it in the first place, such to get the positive feedback, and they don't create a whole family of bad cables that then need to be replaced. They instead get better with each cable that they make. It has been shown that after building a few cables and not getting them to pass PIM, it is learned what's the right way to do it, and once that learning has taken place, progress accelerates. In this particular case, we're showing antennas. It's critical. Another parking lot location, excuse me. In this particular case, we have metal structures around. It, again, was a good location. This particular antenna doesn't use a pigtail. It has a connector on the back, which gave us some advantages. But again, placing the antenna versus PIM is going to be very important. Look, this is again, walk the building, look at the things and see which things may do it. The metal plate that you see behind was a source of potential concern and turned not to be the problem, but again, you need to get a feel for that as you go. If you break the cable, we talked about it, it's more specific on a pigtail cable, which is where the connector is brought out on a small braided cable typically. Improper handling can create PIM. Another classic case of what happens when you don't pay attention to design. In this particular case, the fiber handling conduit was placed in such a way that access to the 4x4 hybrid by a cable was not possible. That, of course, didn't stop anybody from trying to get that thing in there and forcing it to fit. Excuse me. In doing so, the cable was broken, and under dynamic test showed as PIM. Splitters and dividers and hybrids must be properly installed. Try to provide yourself with access to all the connectors so that you can successfully attach the connector. In this particular case, it wasn't easy to do at all. Most common issue is a misconnection of ports. Again, in this particular case, we were able to remedy that without any trouble. Tightening, which is always a problem with all connectors on splitters and particularly hybrids. The problem is the connectors have been put too closely together to allow tool access. You must be able to tighten them, so you must be able to make sure that things get in there. Please put a wrench on both sides if at all possible, such that you don't put stresses on the component that's under being installed. And again, as I said earlier, got to allow cable access without stress. Putting a conduit for the fiber underneath the cable wasn't a particularly clever solution, but it had occurred on a regular basis because that was the method it had been used, and they did not see a problem with it prior to PIM testing. So again, this was a difficulty as going back to try to repair. In a passive test, we talked about breaking it down into a sub-branch level, combine multiple sub-branches into a branch. Again, the reason for a sub-branch is to simplify the system down to where debugging can go efficiently and be done in a way that's logical. Multiple branches will then be combined into the full DAS through the hybrid combiner. In this particular case, the hybrid combiner also serves the purpose of allowing another operator to be added at a later date. So the 2x2 hybrid at the riser level is to allow multiple operators. You can also add another provider with this 2x2 before. Again, we see the 2x2 hybrid used often for this particular situation, and do be aware that the unused ports that are terminated in high power terminations are a PIM source. Antenna placement. You're going to test every antenna location. If you want to assure PIM performance of that antenna location, you're going to test them each. What power level is used is determined by the operator that's asking you to do the construction. Again, high power represents a safety issue. Lower power sometimes is not allowed. Antenna and the environment. We're going to make the assumption that the antenna was tested to be good beforehand. It can be tested on site if you can get into a location, but it needs to be tested in the environment it's going to be mounted in. Final placement is determined by the measurements. Little as 15 dBm, we said earlier, has created PIM in many installations that has caused an entire branch to be useless. A method or a quick tool can be put together. This is a particularly useful version of basically a fiberglass extended rod and a PVC antenna holder, and we'll move the system, the antenna, about with 15 dBm. Make it out of a transparent material. What that basically means is it's going to be something that's not metallic. Again, fiberglass and plastic are good choices. We can figure that out by looking at the return loss if you put an antenna next to it. Get as close as possible to your location where you want to put the antenna. What we're going to be finding is we're probing specifically behind the antenna is what actually is causing the PIM to be created. And so you'll be looking for where is it in this infrastructure before I break in through the sheetrock that is causing PIM above me. Small changes make large changes in PIM. By small changes in location, I'm talking about inches. Quite often less than 3 or 4 inches. Half a wavelength at any given frequency would certainly cause you to go through a large change in PIM. You'll need some methodology, and again, this is where the design team and the construction team need to work together to report where we're going to place this antenna and what's the PIM look like. It is quite possible that you may want to go back to the design team and say this particular area where you'd like to have an antenna has proven impossible to find a location that's not going to cause intermod. 2 by 15 dBm in the antenna, and we get significant results like what you see on the screen here. Here we have a peak PIM by moving it around of 84 dBm, even though we're putting in 15 dBm of RF power. And again, just as another location in that particular building, moving around underneath the panel structure of the building. Each building is going to have a different construction methodology, going to require a different set of learning how things go. And as you can see, we had numerous occasions a minus 120 dBm PIM level, and then moved the location and found it. This is something where a feedback by looking at the screen while you're testing is very critical. Sub-branch test. Again, we're going to move up to the next level of complexity. Each of these antennas has been tested. Again, as the cables were built, they were tested, and the splitters themselves were tested at the factory. So we now have a series of components that should pass if they were constructed together. We'll test that. If that's the case, then we can sign off on that sub-branch. We'll put the low PIM loads in there if we're concerned that the environment is causing a problem. This is another reason to keep the branch to a smaller level. The number of low PIM loads required if you're going to replace every antenna with a low PIM load gets large in a hurry, so you want to test smaller, typically less than 10, to minimize the number of low PIM loads you have to place. Again, limit to a small number of antennas. May be required to measure the insertion loss. We have had experiences where the splitters are put in backwards. This leads to difficulties with the coverage that are harder to catch later on, so typically you may be asked to measure the insertion loss from the input to each antenna just to make sure, again, the sub-branch was constructed correctly. Multiple sub-branches become a branch. We'll go ahead and test those. We talked about earlier a test bed. Here's a MIMO test bed. In this particular case, we brought in, it's a 4-node sub-branch that we've done. This is not the entire picture, but just a picture of the intended 1 node on that 4-element sub-branch. And what you'll see here, we use range to fault, which is the combination of distance to fault, a return loss measurement, and distance to PIM, a PIM measurement, to locate the PIM source. In this particular system, you can see 4 distinct return loss spikes for each of the antennas, which is what you would expect. And you can see there are some responses to the PIM. In this particular case, the largest PIM is located at the second antenna, where we went off and we removed that PIM source and walked back through. This is the advantage of both having range to fault and a test bed to learn how to use the tool available to you in the warehouse. The branch test is, of course, the combination of multiple sub-branches together. Do the PIM test set there, move all the branches together, and we're going to go to the riser level and test. These are all just logical progressions. I'm not going to spend a lot of time discussing it. Then we'll be in the equipment room where we'll do the final test, which will be at the output of the E node B, or the RRU. In that case, you're done with that particular section that's connected there. At that point, you can move to the next RRU. Typical node B. This was a good example of post-construction PIM testing being difficult to accomplish. 7-sector DAS based on fiber fed by an Ericsson remote base station. All those things are good things. RF ports are combined with a 2x2 hybrid. Again, all using DIN connectors coming off the RRU. Then we go to N connectors. Throughout the equipment room, we've got 7/16 DIN connectors. Makes for ease of tightening, makes for good PIM performance where possible. 1/2-inch jumpers and feed lines are all corrugated cable. Again, we mentioned it earlier, but the unused output port of the 2x2 hybrid is a PIM source using a high power 25-watt load. Again, mention the power level of the load you want to make sure that at the test power level of the PIM test set, you are not damaging components. In this particular case, that 2x2 hybrid drops the composite of 40 watts down to 20 watts, and so we're safe there. Typical use of a 2x2 hybrid, this particular one was used in this dash as a step and repeat, so it's always used this way. It combines the DX1 and DX2 of the RRU. The 25 watts was enough to handle the 20 watts under PIM testing. Port 4 is the RF path to the combiner box for the system. We got poor PIM performance of 77 dBm when testing a 2x43 dBm or 20 watts. Remove the sensitivity. There were, under dynamic testing, actually greater levels of PIM created. We found loose connections and tightened those and did the repairs that were necessary. Again, anytime construction is done without PIM testing, it's not unusual to find that you have to go back and do remedial work to improve the PIM performance. 77, 2x2 hybrid is a PIM source. Both output ports are terminated with low PIM loads. This is again where I'm trying to do component level testing. Single component 2x2 hybrid. I found that it was perfectly fine at 112 dBm, 155 dBc under dynamic stress. That's a perfectly good component, and so that's a good result. Acceptable for purpose. High power termination is indeed the problem. In order to remove that from the system test and again simplify the system, we advanced the test point, as we talked about in the diagram initially, beyond the combiner, beyond the 2x2 where the PIM source with the low high power termination, moving it towards the optical modulator. There were additional problems in this particular system. Dynamic test had connectors were finally stable, so in the equipment room we were able to tighten everything and get everything clean. We learned the method by doing it in the equipment room. Again, this was an on-site, on-the-fly learning. PIM source is outside the equipment room, so we began the walk down the RF path to find the problem. What we found is we got two braided cables with crimped-on connectors that were poorly performing for PIM while still running at high levels of RF power. So this is a case where the transition from the half-inch cable that had been used to get from the equipment room to the room where the optical modulators were was followed by poor performing. The half-inch corrugated cable went to the braided cable, carefully selected. Again, we talked about it is possible to find a braided cable. They're typically going to have a soldered outer jacket to keep the braids from moving with respect to each other, which is what causes the PIM. The crimp connectors, crimping as a process has not proven successful with regards to PIM, is the simplest way to say it. That said, one day someone will come up with a way to do it maybe, but not today. Power levels remain high, again, still 10 watts at this location based on the insertion loss measurements. The attenuator is placed before the low power cables is one way if you're going to use attenuators, which is what they did in this particular case, to reduce potential PIM. Dropping the power helps improve the PIM. And they had the high power attenuators in line. Again, they were PIM sources. They were after the braided cable, so we had another set of design related issues. Low PIM load was placed after the inline attenuator. Resistive high power inline attenuators were PIM sources. We were able to measure that without any difficulty. Design might consider using a DAS tray, and we do make one, so this is not a strict plug, but a low power or a DAS tray to go to the fiber optic modulators can be designed such that it's low PIM. It doesn't use discrete components. It is a more compact solution, and we do address the PIM issues because we have our eyes always on the PIM results. We were not able to succeed in this closed system. It remained high at 71. I had further system integration required to identify remaining PIM sources. We never got that particular DAS work, even to this day. Again, review, test the antennas, build a sub-branch, test it, combine sub-branches that have been certified into a branch, test that. Again, each time you're increasing the level of complexity, you need to do a PIM test, bring everything together at the riser level and test. Again, we hopefully are good at this point because all the sub-pieces were good. And then put your equipment room finally together and test it before you go into the customer's RRU. In conclusion, I'm a little bit over time. I apologize. Good design is required. No contractor team, no matter how good, can make a bad design work. You must know what you're doing. On-the-job training is a disaster. It's a painful disaster, and it's usually a sleep-deprived disaster. DAS design and construction is complex. There are a large number of components in every given DAS, and anytime it's on the RF path, it's a potential PIM source. This makes for difficulty. Have a plan and refine it, as we talked about. Find poor PIM components in construction by simplifying the systems. Always break it into pieces. There is only logic and then the use of range default in some cases to aid you in finding out what's going on. Again, first pass success is huge in that case. Clean and then clean again. The amount of material that creates PIM is very, very small. Quite often what we'll see is that the alcohol wipe used to clean the thing goes black, but it's nothing physically as large as what you saw from the grains of metal. Tighten everything to specification. Check to see that that specification for that particular connector is meeting your requirements. Do be aware of the type N connector, when over tightened, will fail both PIM and return loss, so don't over tighten, but tighten to the proper specification. Make sure you practice that. You cannot over communicate the results. At this point in the evolution of PIM testing in the DAS, there are more questions than answers. By sharing the information for all the results that you get, everyone moves a bit forward. A lot of those results were gained over the course of testing in North America and South America, and we're still moving forward. And I can tell you at this point in time that no one has a complete handle on how to do PIM good DAS systems every time in a short period of time. appreciate the time that you spent. We'll now open the floor for questions. Thank you very much.
Thank you, Tom. Appreciate that. Okay, we'll start tackling some of the questions now. First one, PIM through a diplexer or EHCU?
Through a diplexer, what you're going to look at, again, if you go back and look, we're transmitting 2 test tones. They're typically going to be in a single band. You need to make sure that the diplexer port that you're testing will transmit or pass the test tones. It will also need to be able to receive, because the PIM that we're measuring is a reverse PIM, it will need to receive any of the receive channel coming back. So if, for instance, I've got a diplexer combining a high band signal and a low band signal, I can test the high band port with a high band PIM test set, but I have to then test the low band side of that filter with a low band PIM test set, because that's where the RF signals can actually get through the system.
Okay. Couple of questions on outside interference, one specifically on medical equipment. Just maybe you want to touch base on some of the outside interfering sources.
Sure. Medical equipment is a good example. We find a number of occasions where we also have people using wireless phones or cordless phones from outside of the market they were sold in, and so the bands are walking on top of each other. Typically all these are found by using a spectrum analyzer. The Kaelus gear offers a spectrum monitor port, which allows you to see outside interferers that are CW or pop up, but it's not as full-featured as a spectrum analyzer. But there's a large number of sources. Again, a Canadian operator found that there were fans built into the air conditioning vents that were actually a source of PIM. We have seen PIM generated from, I call them the cone of silence, but there's a product out there that uses noise cancellation mechanisms to cancel out noises in a cube environment where it's got a lot of concrete ceiling, and so they add these noise silencers and they cause PIM. LED ballast for green systems have created intermod. Most often though the intermod that's an outside, and those are outside interferers in all fairness, because a motor, the brushes if you would, are creating the noise. The ballast and the PIM generator, or the interference generator from that, was all caught by just doing measurements. Quite often the same methods you would use in a macro system of walking around the facility with an antenna, and a spectrum analyzer is still going to be used. Again, creating a team that can debug that's a very challenging thing to do. But get your PIM out first, because that's self-inflicted. And you'll notice that by not turning on the PIM test set and looking through the spectrum analyzer. And so you'll find your other interferers.
Okay. Here's one. What example location of the wrong, on page 20, sorry, the wrong antenna placement resulting in PIM, and how about the cable placement if we have the same shaft feeder on the power electrical cable? Not sure if that's...
Okay. I'm going to repeat that one more time, and I'll see if I can sort that out.
Example location on page 20 of wrong antenna placement resulting in PIM, and how about the cable placement? Like, is the power electrical cable, does that have an effect on it?
Yes, it can. Again, the conduit, I guess I'm getting this. The conduit itself, and whatever type of conduit, there are a couple of different types of conduit, if it's exposed to enough RF energy. Typically what I would do in a situation like that is either take, again, the still wool is an excellent example of a PIM source. If you believe that, say, a piece of conduit is potentially creating PIM, if you put a PIM source, jingling keys or steel wool, at that location, you'll be able to determine if the RF field is high enough to create PIM. We have had a number of experiments where what we've done is either relocate the antenna, reorient the antenna such that the suspected PIM source, whether it be conduit or something like that, which can be PIM, is moved from the field of view of the antenna, or absorber. So there's a number of methods, but again, this is the early days of trying to sort out what can we do, and it's usually the location of the antenna and being able to look at the environment and determine which pieces. And again, it varies each time that you do it.
Can we expect different network improvements versus different technologies? Is there any difference between GSM, UMTS, LTE?
Absolutely. Absolutely. The good news is GSM is less affected by intermod, and designs can possibly be made such that it's much more robust against it. The difficulty, unfortunately, is no one believes that GSM is the preferred method going forward of interfacing to your customers, that they're going to be data hungry, and that LTE is which is the direction things are headed. So current DASs that are being constructed to support multiple LTE vendors at multiple bands, and LTE is the most sensitive to the intermod. And we found a number of, another example, CMA providers see that they can determine there's PIM impacting their system, but they find that it's not nearly as big an impact as it is in the LTE system. So everybody who's moving to LTE or anticipates that their DAS might one day support LTE with multiple providers is going to need to address PIM as early as possible. In some cases, we have had operators turn off their GSM such that their UMTS will work, because the GMTS and the GSM were actually interfering with each other. The frequencies that they were using were such that they were creating intermod on that particular DAS. So yes, GSM, a straight GSM system, is more robust because of the technology versus PIM, but it's also limited in its capability to provide data throughput.
Okay. As far as equipment specifications, looking at like a neg 140 DBC spec versus something that's higher like neg 155, do you see a big difference between the two when you're doing your testing and low power DAS systems?
Yeah, and that's going to be one of the things where, again, the evolution of the industry over the last 20 years has been such that previously the test power level was not specified. When the IEC got together and set an international level of 2 by 20 watts, it was to help allow that conversation that you're, in a sense, asking to, we're all testing at the same power level, so I can compare my DBCs to your DBCs. What we're seeing now is, do we need to have that same level of testing? Some operators are saying, yes, you still need to be testing at 2 by 20 watts and then get the 155 type DBC numbers for every component in your system, your string. And others are leaning towards, well, maybe I can give my vendors some slack by testing at a lower power level, but I still need at the end of the day for LTE to have a noise floor below 125 dBm. That's really what they're looking at, is to give them a little bit of margin below the noise floor that they know their system can see. So when you start thinking about where are the signal levels and talking dBm, you'll find that the answer is always, I need to have my components, my PIM from my components and from my system well below the -125 number. So that's not a direct answer, because again, when you say DBC, you're implying something that you didn't say thereafter, which is what's the power test level.
Oh, yeah, yeah.
So the power is sensitive, and there will be stuff, but the in-game, if you're talking to an RF engineer, he's looking to keep all of his interfering signals below 125 or so dBm, or even lower.
Okay. Specifically talking about stadium deployments for DAS, are there any specific PIM test things to look out for in stadium testing?
All the same sorts of stuff. There's a little bit of a change. My experience with the stadiums is not as extensive as my in-building experience, so I'm going to be speaking a little out of turn here. But it's much like doing a macro system. You're going to have all the same, when it comes to PIM, the same thing is always going to be said. Clean and tighten are the two keys that are first and have the right components. And then it's going to come down to placement in the environment. Quite often what we see in bigger arenas is that the antenna is placed in such a way that it's really in an environment that it creates PIM at the antenna. So that's usually the two things that happen. The good components are there. Make sure you've got access, and then go forward as if it's really, in all fairness, like it's a macro site.
Okay, as we are running a little late, I'm going to narrow it down to just two more questions. So one is specifically talking about the lower power levels, and why do you think many in the DAS space are not aware of this, that you can see PIM at 15 or 20 dBm, you know, and not, you know, higher power levels, that you see them on a macro site?
Yeah, I'll tell you exactly how I figured it out. I didn't believe that I needed to test at the lower power levels either until I went into a site and actually did the work. We had a number of operators, specifically in Canada, who embraced PIM and said we need to understand, and they started off testing like everyone else was testing at 2 by 20 watts and found they were having a great deal of difficulty. Plus they were having issues with the components at the antenna level being available that can handle the 40 watts of composite power. And so they started dropping it. And once they started dropping it, they've been able to go down as low as under 10 dBm and still see PIM. So they're saying that if they want to deploy a system without having to test PIM, it's going to need to be around 7 dBm of transmit power before they feel comfortable that any PIM from components or environments that they've seen will be such that it doesn't affect the performance of the system they're deploying. So it's mostly just experience, is I guess what I would say. I was of the opinion and hope that by testing at the lower, or having lower power levels from, say, a remote radio head, that I'd be in a much better place, but it's turned out not to be the case. That again, the LTE sensitivity and the fact that apparently PIM is easier to generate than we had expected has led us to experience that's shown that we have to test at lower power levels, or it is sensitive to lower power levels. Now everyone tests at a higher power level once you get back to the actual input to the system and to the DAS where the BTS is.
Have you seen manufactured braided cables that have better performance in PIM?
Absolutely. In my history, I used to design lots of antennas, and as antennas became more complicated, it was necessary for us to find braided cables that were tinned that could pass PIM. Now the difficulties with every cable and anything that is going to be used or considered for PIM is survivability across the environment at the time, the stresses that get put on it. You can, and again, your friend the internet will help you find cables that do pass PIM that are braided, and I believe all of them at this point in time are tinned when they're done. Again, the design work I've done for low-loss cables, it's quite, I won't use the word easy, but what you're looking for in the case of a braided cable is you want to have a copper center conductor with a silver plate. Anything else is a steel center conductor is going to have difficulty meeting PIM. And then the braids, the percent coverage plus the soldering is what gets the rest of the stuff done in the outer conductor. But everybody's trying to move the ball forward on this, so what I say today will be outdated sometime next week, I'm sure.
Well, thanks a lot, Tom. Thanks a lot, Brent. I really appreciate this. And anybody that did send a question that we didn't get to, we will follow up with you. And if you have any further questions, please feel free to contact us. And thanks again, everyone.